Okay. Hello, hello, all of my beautiful AP Calculus students. In this video, we will work through the solution of a single part of each of 4 different FRQs from previous AP Calculus exams. In each question, a differential equation and an initial condition is given. Example 1. Find an expression for h in terms of t given dh dt is equal to negative 1 over 10 times the square root of h, and h equals 5 when t equals 0. So I'm going to read that one more time to understand what it's asking me to do. Find an expression for h in terms of t. H in terms of t. So I'm looking for something that says h of t equals question mark. This is what they want, this question mark right here. And over here they give me what's considered an initial condition. So they are telling me that h of, let me see, t, which is 0, h of 0, is equal to 5. This gives me an xy coordinate point of 0, 5. And actually, in this case, it's not xy, it's going to be t, h. Okay, so 0 is my time, and h equals 5 for whatever that is. And I'm just presuming that t is time because it always is. All right, so I want h in terms of t. They gave me dh dt, so they're giving me a derivative. This is a differential equation because I have a derivative embedded in the equation. In order to undo that derivative, I'm going to have to do an antiderivative, or what's also known as an integral. But I can't integrate both sides of my equation yet because I have a mixture of variables. So at first, I need to separate my variables. Step 1 is going to be multiply both sides of this equation by dt, so that dt here will cancel off, or divide off, whatever you'd like to say, with the dt on the bottom. This is going to leave me with dh equals negative 1 over 10 times the square root of h dt. That's all good and well. At least I got rid of the t that was on my left-hand side of the equation. My goal is to have only h on the left and only t on the right. So I definitely have just my h on the left. However, on the right-hand side, I do have an h in there. I need to get rid of this square root of h that's on the right-hand side of my equal sign. So I am going to divide both sides of the equation by the square root of h. I'm going to simplify this down, clean this up a little bit here. And I'm going to say h to the negative 1/2 dh is equal to negative 1 over 10 dt. And now I definitely have my h factors, my h variables, however you want to consider it, on the left-hand side of my equal sign, and my t's are on the right-hand side with the constant, which is where I'd like to keep my constants anyway, on the right-hand side with the t's. So I need to integrate now. And I know most of you would simply put an integral sign on both sides of your equation like this. However, I'm not going to do that. I'm going to write it out nice. I'm looking at the integral of h to the negative 1/2 with respect to h is equal to the integral of negative 1 over 10 with respect to t. On the left-hand side of the equation, I'm going to integrate h to the negative 1/2 with respect to t by using the simple power rule, which means I'm going to add 1 to my exponent and divide by that new result, giving me h to the 1/2 divided by 1/2 equaling, and when I integrate the constant negative 1/10 with respect to t, I get negative 1/10 t plus my constant of integration, which I will solve from the initial condition that was given to me up on top over there. All right, let's clean this up slightly. When you divide by 1/2, that's the same thing as multiplying by 2, so I'm going to call that 2h to the 1/2 is equal to negative 1 over 10 times t plus my constant of integration. And I could stop right there, use my initial condition, solve for c, and plug it back in. However, I think I will divide both sides of this equation by 2. Since I already have a fraction, you see this fraction, negative 1/10, I certainly wouldn't create a fraction at this point, but since I already have one, I'm not going to be making anything too much more complicated by dividing by 2. So h to the 1/2 is equal to, I'm going to take negative 1/10 and divide it by 2. That's going to give me negative 1 over 20 t plus, and I know that when I take this c value and divide by 2, I get a different c value, but one c value is the same as an x for me. I know that some people might want to call the first c that we put into the problem c sub 1, which stays c sub 1, and then this would be a different constant, c sub 2. Although a c is a c to me, so I'm just going to leave it plus c. And that's mathematically acceptable in this calculus. So let's see. Let's bring this up over here together with our initial condition. I'm going to write up here that this is the initial condition. So using now that initial condition, 0, 5, I'm going to take this h to the 1/2 equaling negative 1 over 20t plus my constant, and I am going to substitute the h and the t, and I am going to solve for c. I like to write my parentheses before I do my substitution. Those of you in my class, you know that about me already. It eliminates a lot of copying errors and silly mistakes. So let's see, my t is 0, so I'm going to put a 0 in for t, and my h is a 5. I'm going to put 5 in here. I'm going to clean this up a little bit. I'm going to talk about 5 to the 1/2 as being the square root of 5 is equal to negative 1 over 20 times 0 is 0, and then 0 plus c is just c. So c is the square root of 5. I'm going to take that together with the equation that I substituted my initial condition into. So I'm going to take that with my h to the 1/2 equaling negative 1 over 20t plus, and now I know my c value is the square root of 5, so I'm going to put the square root of 5 in there. And I need to solve for h. H is to the 1/2 exponent right now, so in order to undo that 1/2 or square root, I simply need to square both sides of the equation. So that will yield h equals, and I'm going to take negative 1 over 20t plus the square root of 5, and I am going to square that entire right-hand side of my equation. Okay, and I do believe that is going to end the question right there. We don't have to do much more. We could circle or box just the right-hand side of this equation, or you know what I think I'll do? I think I'll just write h of t is equal to, open parentheses, negative 1 over 20. I want to make sure that looks like a negative sign too. I don't want anybody confused on that. T plus the square root of 5 quantity squared. And I think we will box that as our final answer and say question 1 is done. We have found an expression for h in terms of t with the initial condition that they posted, that h equals 5 when t equals 0. Okay, so much for that. That didn't hurt too bad, right? Let's move on to example 2. Example 2 is here. Find an expression for g of t that satisfies the differential equation dg dt is equal to negative g minus 27 to the 2/3 with the initial condition that g of 0 equals 91. Evaluate g of t at t equals 3. So we have one extra step here. Let's see, I do have the initial condition that g of 0 equals 91, so that'll mean when t equals 0, my g is 91. All right, well, we have this differential equation, it's hard to say this, huh? dg dt, and we have got to separate our variables before we integrate, so we're going to multiply both sides of this equation by dt. This will eliminate my denominator. Say goodbye, and I just have dg now is equal to negative, open parentheses, g minus 27 to the 2/3 dt. All right, I got my t out of the left side of the equation, but now I need to get the g out of the right side of the equation. I can't just pull it out of a set of parentheses where something is being subtracted and then that whole quantity is being raised to the 2/3. So I'm going to literally have to divide both sides of the equation by g minus 27 quantity to the 2/3 to make that disappear. And what I do to one side of the equation, I must mimic on the other to maintain the balance of the equality. So g minus 27 to the 2/3. And now we're going to clean it up. This is going to give me g minus 27 to the, yes, you guessed it, negative 2/3 dg is equal to negative dt. So I think we're ready to integrate. We got our g variable on the left-hand side of the equation, the t variable on the right-hand side of the equation. We're ready to go. So we're going to go ahead and put our integral signs in here. And like I said, you'd love to just go like this, and I would love it too, but I'm going to write it over again. The integral of g minus 27 to the negative 2/3 dg is equal to the integral of negative dt. And if it makes you feel better, you can put -1 in there. That suffices as well. All right, when we integrate, we're going to have a basic power rule here. And also, I don't really have to pay too much attention to the chain rule. Maybe you guys should think about that for a minute. I could go to the side and talk to you about it. As a matter of fact, I think I will. Let's just roll to the side here for a minute and talk about the integral of g minus 27 to the negative 2/3 dg. Now this g thing drives me crazy, so just for the sake of arguing this right now, I'm just going to replace my g with an x, so I'm more comfortable. So I'm going to go to the side here and I'm going to say let u equal x minus 27. And that means my du is just plain old dx. So this integral becomes u to the negative 2/3, yikes, du. So here I am. This is my u and this is my du. And when I integrate u to the negative 2/3, I simply use the regular power rule. This is u to the 1/3 divided by 1/3. Of course, we have a plus c on the end of that. This gives me 3u to the 1/3 plus c. Everything's good there. And I suppose you could bring that u back in. This gives me 3x minus 27 quantity to the 1/3 plus c. So I am going to erase all of this information on the right-hand side that I put there, but I just want you to see that over here on the left, you see this g minus 27? Because the derivative of g minus 27 with respect to g is just 1, I really don't have to play with this U-substitution. I can just think of this as being like an oogie boogie, some big quantity that's being raised to the negative 2/3. It is my u. It's the inner function, but the derivative of that inner function is a 1. So I would just do something like g minus 27. I would add a whole to negative 2/3. That would give me negative 2/3 plus 1 is a positive 1/3. And I would divide by 1/3. Can you see how this would be the same down here? Because dividing by 1/3 is going to end up showing a multiplication by 3. And my g and my x match. Of course, my plus c is going to end up on the right-hand side of the equation. So everything is okay there. This will be equal to the antiderivative or the integral of -1 with respect to t is just -1t. And then my constant of integration, so the left and the right together are merging on this constant of integration right here. And I'll put my plus c on the right-hand side. Okay, I hope everybody gets what we just did. If not, you can rewind the video. Play it again, Sam. All right. All gone. Isn't that nice? Let's clean this up. This is 3 times g minus 27 to the 1/3 is equal to negative t plus c. And let's see, I would love to divide by 3, but dividing by 3 would put a fraction in my problem. So I'm going to choose not to, and I am going to use my initial condition here. So what is my condition, my initial condition here? Using the initial condition that g of 0 equals 91. That means that when t is 0, my g is 91. So let's take this function that we found here by integrating. Let's say 3g minus 27 to the 1/3 is equal to negative t plus c. And we are going to solve for c. 3, I'm going to wait on my g there, equals negative t plus c. Now when t equals 0, so I'm going to put a 0 in for t, g equals 91. So I'm going to put a 91 in for g. I'm going to simplify down here. Suppose you could go to the side and do 91 minus 27 if you don't know it off the top of your head. Let's see, 91 minus 27. Hopefully everybody can come up with that 64 right here, which is nice because 64 is a perfect cube, which means I'm going to be able to cube root it beautifully. This is equal to 0 plus c, because negative 0 is still 0. This is 3 times 4, which is c. That means that c is 12. We've got a nice c value here. All right, I'm going to take that c value together with the equation that I used to substitute the c in, which is still right here. So I'm going to bring it right here. I'm going to bring that c right here. 3 times g minus 27 to the 1/3 is equal to negative c plus 12. Now we might have a little bit of work to do here. Negative t, I'm sorry. Negative t plus 12. Going to have a little bit of work to do. Let's see what we're going to do. We need to solve for g. I think the first thing we can do is divide everything by 3. I knew we were going to have to get stuck doing that at some point. Let's get rid of that over here. Okay, so we're going to divide both sides of the equation by 3. This is going to give me g minus 27 to the 1/3 is equal to negative 1/3 t plus 4. Is everybody okay with that? Hopefully. And now I need to get this g minus 27 alone, so I need to undo my 1/3 exponent, which means I need to cube both sides of the equation. This will give me g minus 27 is equal to negative 1/3 t plus 4 quantity cubed. And now all I have to do is add 27 to both sides of the equation and I'll have my g. I have g equals, and you know, I think I'll drop down a line here just to make things nice. Negative 1/3 t plus 4 quantity cubed and then plus 27. And that I can refer to as my g of t. I mean, this function g is a function of t, so I suppose I can just call it g of t if I'd like to. And I think I will. Let's go ahead. G of t is equal to negative 1/3 t plus 4 quantity cubed plus 27. Okay. I think that finishes one part. It says find an expression for g of t that satisfies our differential equation with that given information. So this is one of our, oh, tell me that didn't just happen. Look how I was able to just push that back button. Alrighty. Now the second part of our question says evaluate g of t when t is 3. So now I want to put a 3 in here. I'm now looking at g of 3 is equal to negative 1/3, there's my t, plus 4 cubed plus 27, and the t value is 3. Okay, g of 3 is now negative 1/3 times 3 is negative 1 plus 4 cubed plus 27. One step at a time. I know a lot of you do this all right in your head, but then that's how you make mistakes, right? So negative 1 plus 4 is 3 cubed plus 27. 3 cubed is 27. And 27 plus 27 is, you guessed it, 54. And that ends the second part of the question. Okay. Make sure that we've read everything and done everything we're supposed to do. We found an expression and we evaluated g of t when t was 3. Okay. Question number 2 is done. Example 3. Consider the differential equation dy dx equals e to the y multiplied by the quantity of 3x squared minus 6x. Find y equals f of x, the particular solution to the differential equation that passes through 1, 0. So this 1, 0 here is called my initial condition. It is what is going to allow me to solve for that constant of integration, that plus c that we'll eventually put into our problem. Okay, well we have dy dx equals. This is a differential equation, obviously because there's a derivative embedded in the equation. I want to find y equals. So in order to get y equals, I'm going to have to undo that derivative, which means I need to integrate. However, I have some mixed up variables here, so I need to separate my variables before I can integrate. I want all my y variables on the left side of the equation and all my x variables on the right hand side of the equation. So let's eliminate this dx right here from this denominator first. Multiply both sides of the equation by dx. This gives me dy is equal to e to the y times the quantity 3x squared minus 6x dx. And now I'd like to remove the y variable from the right-hand side of the equation. However, it's attached as an exponent on the e. So e to the y is a factor on the right-hand side of the equation. I'm going to divide by that factor to make it go away, and it'll divide by the factor on the left-hand side of the equation as well, and it will bring that factor to the left. I'm going to clean this up and call this e to the negative y dy is equal to the quantity of 3x squared minus 6x dx. Okay. Oops. There we go. Lost my minus sign, didn't I? There we go. We're set to go. Now I can integrate both sides because the only variable I have on the left side of my equation is a y, and the only variable I have on the right-hand side of my equation is an x. So my variables have been separated. I'm going to integrate both sides of the equation, and I know you would like to just write integral signs like that, but I'm not going to. I'm going to put my integral sign down here. E to the negative y dy is equal to the integral of the quantity of 3x squared minus 6x with respect to x. Alrighty, the right-hand side looks pretty simple, and the left-hand side actually looks simple as well if you're used to playing with exponential functions. Let's see. I'm going to go to the side for a second and just review a couple of things with you. The derivative with respect to x of e to the x is itself e to the x. That should be no problem. The derivative with respect to x of e to some function of x would be e to that function of x, but then you'd have a chain rule here multiplying by the derivative of that function of x. So for example, the derivative with respect to x of, let's say, e to the 5x would be e to the 5x multiplied by 5, the derivative of my exponent. Okay, so that being said, and I know, let me say one more thing. I think that most of you probably have seen this idea brought out like the derivative with respect to x of e to the u as equaling e to the u times u prime. So you've probably seen it written like that. Some people see it as e to the u du. However it is, it goes around that way. And if you're going to take the derivative and get these answers, well then you can integrate these answers and work backwards to get your function that you took the derivative of. Well, that being said, this is all pretty good. If this were the integral of e to the y dy, well then this answer would just be e to the y. But it's not, and I can't ignore it. All right, because I have something other than a basic y on my exponent up here. This is not the situation. However, let's just go to the side one more time over here and see what something means here. What if I asked you to take the derivative with respect to y of e to the negative y? What if I asked you to do that problem? I'm hoping you would copy e to the negative y and then take the derivative with respect to y of this exponent. And the derivative of this exponent with respect to y would be a negative 1. So this answer would be negative e to the negative y. So that would be kind of nice. That means that if I were to want to go backwards and integrate negative e to the negative y with respect to y, I would be clear in just saying that answer had to be e to the negative y, the thing that I started with a long time ago. Yeah, unfortunately I don't have this negative sign. And when I say this negative sign, I'm talking about this negative sign right here. You see this one? It doesn't exist over here. If it did, I would be good to go. Well, in what we're playing with right now, we could go ahead and put a negative sign in here. We could create a negative sign and attach it to the left side of our equation, as long as we attach another negative sign on the left side of the equation. Because two negatives multiply to make a positive, which means I'm not really changing the left side of the equation as far as its value goes, but I am changing its appearance in order to make my integration applicable real fast. So the negative integral of negative e to the negative y dy becomes, and you just copy this negative sign, and e to the negative y comes down. And it's that simple. All right, well, I know that most of us are not going to consider it that simple. So I'm going to go through a little something with you to do this a little bit better here. I'm just going to leave that answer where it is, but I am going to come over here and I am going to say, let's erase all of this stuff I wrote here. And if you still want to see it, you can just back up your video and watch it again. So I am going to take e to the negative y, the integral of e to the negative y with respect to y, which was my original equation, and I am going to do a U-substitution with this. So I'm going to say let u equal negative y. This exponent right here becomes my u. That means that du equals negative dy. But I don't have a negative dy, I just have dy. So I'm going to divide both sides by -1, and I'm going to get negative du is equal to dy, which means this is negative du. I'm going to rewrite this integral in terms of u's. This now becomes e to the u multiplied by negative du. This negative now can be moved to the outside of your integral like any constant can. So I end up with negative the integral of e to the u du, which says integrate e to the u with respect to u. That's just basically plain old e to the u, and this negative sign comes down. You just carry it. And of course, when you do an integration, you should put a plus c for your constant of integration. Now let's put our u back in. This is e to the negative y plus c. And isn't this exactly what we put over here on the left-hand side, minus the plus c? Of course, we're not going to put the plus c because both sides get a plus c, and we'll merge them together and we'll only write it on the right-hand side. So I'm hoping that you understand that the integral of e to the negative y with respect to y is negative e to the negative y. That's probably kind of tricky in this problem. Not if you work it all out, not if you show your steps clearly, and especially not if you have an intuitive understanding with the chain rule. That makes life easy. Let's move back over here and integrate the right-hand side of our equation with respect to x. I am looking at integrating 3x squared minus 6x. So I'm going to copy my 3, and when I integrate x squared, that becomes x cubed divided by 3. Copy the minus 6, and when I integrate x, I get x squared divided by 2, and then plus c for my constant of integration. Let's clean this up a little bit. Negative e to the negative y is equal to, my 3's divide off, I get x cubed minus 6 over 2 gives me 3 as my coefficient on my x squared, and then plus c. And I think I will divide everything by -1 here, although you don't need to. I'm just going to clean it up a little bit. E to the negative y is equal to negative x cubed plus 3x squared, and I could say minus c right here because I know that if I want to keep the same c value, yes, it's a minus, but I really don't care because I haven't solved for c yet. So when I solve for the c, I'll put it back into this equation right here. Does that make sense? I hope so. All right, well, let's take this now and bring it back up with the initial condition. So I'm going to bring this up here, and I'm going to say using that initial condition, which is the point 1, 0. Let me copy my equation. I have e to the negative y is equal to negative x cubed plus 3x squared plus c. Now I don't like to take a step as soon as I draw this arrow, so I always want to copy what I had before, and plus I always like to see the equation directly above where I do any substitutions. So e to the negative something equals negative something cubed plus 3 times something squared plus c. My input for my x is a 1, so there go my 1's, and my y value is a 0, so there's my 0. So negative 0 is still 0. And copy this negative sign. 1 cubed is 1, plus 3, 1 squared is 1, and plus c. E is a non-zero base, so e to the 0 equals 1 equals negative 1 plus 3 plus c. Negative 1 plus 3 is 2. And I've learned my lesson here. I always want to write this last piece out because it's be just like me to mess up right here. Negative 1 is equal to c, or c is negative 1. I'm going to take that c value and I'm going to bring it back here. So I'm going to rewrite my equation. E to the negative y equals negative x cubed plus 3x squared minus 1. See how that c value came down in here? Alrighty. Let's just do that. Very good. Now my job is to solve for y. It's not that big of a deal. The y is up here. It's definitely part of my x. It is my exponent. The negative y is my exponent. So the y is part of my exponent. And you know that a logarithm is an exponent. So we definitely have to play with logarithms to get that exponent down. We could apply the natural log to both sides of the equation, or we can do that in all in one step and just say, hey, this is exponential form right now. Let's switch it into logarithmic form. This gives me natural log of base e, of course. I don't have to write that, of negative x cubed plus 3x squared minus 1 is equal to negative y. I'm going to turn that around because I want the thing I'm solving for to be on the left-hand side. Negative y equals the natural log of negative x cubed plus 3x squared minus 1. And I'm almost done. I just need to divide everything by negative 1. This gives me y equals negative natural log of negative x cubed plus 3x squared minus 1. And I do believe that wraps up our problem. Let's just take a peek here, make sure we did everything what we were supposed to do. Consider the differential equation, do I dx, da 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 da. Find y equals f of x. Now y is a function of x, very good. The particular solution through 1, 0. Okay, I think we are good. Everything looks good, and that means that question number 3 is complete. Example 4. Given dB dt equals 1/5 multiplied by the quantity of 100 minus b, where 0 is less than or equal to b is less than 100, use separation of variables to find the particular solution. Yeah, you can't see that, can you? Hold on, you guys. There you go. Use separation of variables to find y equals b of t, the particular solution to the differential equation with the initial condition of b of 0 is equal to 20. So I wrote my equation down here, my differential equation, which is a differential equation, obviously, because it has a derivative embedded inside it. Let's backtrack just for a quick second. What does this mean, b of 0 equals 20? I'm hoping you know what it means by now. This is the initial condition that allows us to solve for c so that we can write our y equals function in terms of t. Okay, so let's move on here. I want to integrate both sides to undo this derivative, but I can't integrate because my variables are mixed up, which means I need to separate my variables nicely. I would like the only variable on the left-hand side to be b, and I would like the only variable on the right-hand side to be t. So we are going to multiply both sides of this equation by this denominator and eliminate that dt from the left-hand side of the equation. Very nice. This gives me dB is equal to 1/5 times 100 minus b dt. Now I know you kind of think, let's multiply that out. I can get rid of those parentheses. That's something I know how to do. Well, you might know how to do it, but it's not something you should do, because we need factors in order to divide our factors to the other side of the equation. We can't move terms back and forth. We have to move factors back and forth. So this b is embedded inside this set of parentheses with 100 minus b. I'm going to divide both sides of this equation by that factor, 100 minus b. Divide by 100 minus b. And this is, you know, it's a good time to say this to you, everybody. Never add or subtract a term back or forth when you're trying to do separation of variables. It's always multiplication or division. Always, always, always. Never add and subtract. Okay? So for right now, we are looking at, let's see, let's clean this up a little bit. 100 minus b. Can I call this to the negative 1? dB is equal to 1/5. This divides with this, and I just have dt. Okay? So as of now, the only variable on the left-hand side is b, and the only variable on the right-hand side is t. So I am good to go to integrate. And yes, I know, you all want to do this little woo-hoo, but I'm not going to let you do that. Actually, I can't stop you, can I? But I'm not going to do it here. I'm going to rewrite my integral. I'm going to write 100 minus b to the negative 1 dB is equal to 1/5. Oh, sorry. What did I lose? There you go. 1/5 dt. Very good. Okay, so I'm thinking this looks like it might be a regular power rule, that I just add 1 to my exponent and divide by my new exponent. But if I take this exponent, which is a negative 1, whoops, Gina didn't mean to do that. If I take this exponent, which is a negative 1, and I add 1 to it, won't that end up giving me 0? And then I'd have to divide by 0. So that's not even allowed, is it? Can't divide by 0. Division by 0 is undefined. So something else is in play. I think I'll be better off looking at this if I consider this the integral of 1/100 minus b dB is equal to the integral of 1/5 dt. Now that whole conversation I just had with you about trying to integrate something to the negative 1, I've had that conversation before in the past, and so has everybody else. That is the only time when your power rule won't work, and that's where natural logs come into play. So let's go to the side here and just review for a minute. If I asked you to take the derivative with respect to x of the natural log of x, you should remember that this is 1/x. If I asked you to take the derivative with respect to x of the natural log of some function of x, you should know that this is 1/x multiplied by the derivative of that function. So, for example, if I told you to take the derivative with respect to x of the natural log of 3x squared, well, let's just say 3x, then it would give you 1/3x times the derivative of 3x, which is just 3. And many of you are really used to just not even putting the times 3 on the side. You just put the 3 right on top and then simplify. So this is true. All right, we got to multiply by that derivative. That's the chain rule right here. All right, that being said, some of you have seen this before as, I'm going to erase this example, natural log, take the derivative with respect to x of the natural log of u, and that's 1/u times u prime. Some people call this u prime over u. All right, so I'm hoping, just like I did in the last one, I hope that when I look at this denominator here, this 100 minus b, you take that derivative of 100 minus b, and you think to yourself, it's too bad that the numerator doesn't say -1 right here. Because if it did, if the derivative of the denominator were sitting on the numerator, then I could just backtrack that integral, and I could say, well, that's just natural log of 100 minus b. But there is no negative sitting there. Intuitively, I would want you to put a negative there and put another negative on the outside of your integral to counteract that negative that you've applied, because two negatives multiply to make a positive, which means your value of the left-hand side of the equation does not change, just its appearance. And then you would be able to integrate this and just say, okay, I'll copy my constant right here. This is natural log of the absolute value of 100 minus b. And you'd be done with that question right there. You'd have exactly what you need. All right, I'm hoping that that's what most of you can do. This is equal to the integral of the constant 1/5 with respect to t, which the answer to that is just 1/5 t plus c. Okay, so is there anybody that would like me to go to the side and do a U-sub for that problem? And I know someone's saying, yeah, show me what the U-sub would look like for that. So I am going to do that. Let me erase this information. I'm going to go back to the original question on the left-hand side of the equation, which is the integral of 1 over 100 minus b db, and we're going to db, and we are going to do a u-sub for that. We're going to say let u equal 100 minus b, and then du would equal negative dB. Well, I don't have a negative dB. I have just dB. So in the previous example, same thing happened. We're going to do this here as well. This 100 minus b, this is like my u, and my dB, I need to solve for dB. This is negative du is equal to dB. Come up here, circle the dB, and call it negative du. This now becomes the integral of 1 over u multiplied by negative du. This negative comes on the outside, and I have 1 over u du. The integral of 1 over u du is just natural log of the absolute value of u plus c. And what was u? U was 100 minus b. And again, the plus c, which I'm not going to incorporate over here on my left-hand side of the equation. But can we understand? Do you see how this and this are absolutely identical? Okay, so whether you have to work it out long or whether you can be more intuitive and see the chain rule would provide a negative sign that you'd need, either way, work that thing out, get your correct integral. All right, I'm going to eliminate this, and we are going to continue up there. Alrighty, so let's see. I think I will, just from right here, I'll say using, and what was that initial point again? Was it 0, 20? 0, 20. Notice how I say that? 0 is my input, 20 is my output. So 0 is my t, and 20 is my b. So 0 is my t, and 20 is my b. So using 0, 20. I get negative natural log of the absolute value of 100 minus b equals 1/5 t plus c. My t is 0 and my b is 20. Oh, sorry. This gives me negative natural log of 100 minus 20 is 80. That tells me that my absolute value symbols are useless right there, right? This is 0 plus c. Negative natural log of 80 is equal to my c value. So knowing that, and knowing the other piece of information, let's see, let's take this where I actually had my c, and let's take my new c value. Let's bring it up here, up here. I'm going to say that my negative natural log of 100 minus b is equal to 1/5 t plus c. I'm now going to rewrite this, and I am going to put that c value in its place. And the c value is negative natural log of 80. So negative natural log of 80. Sorry about that. Okay, so far so good, I hope. I'm going to get my natural logs together so that I can use my properties of logarithms to make just one logarithm. So I am going to add the natural log of 80 to both sides of the equation. Add natural log of 80. I'm going to add natural log of 80. And this is going to give me natural log of 80 minus the natural log of 100 minus b. Now, I'd like to get rid of these absolute value symbols here just so that I don't have them. And I did give you a restriction on b, didn't I? Way up at the beginning, I said that b was in between 0 and 100. So if b is less than 100, doesn't 100 minus b absolutely have to be positive? So I think it does. It definitely is. So I can just write 100 minus b with parentheses equals 1/5 t. Now my logarithms are being subtracted. That means my exponents are being subtracted. That only happens when my powers are being divided. So I'm going to have natural log of 80 divided by 100 minus b, and that is equal to 1/5 t. I don't want to call that 0.2, just because I'm about to switch into exponential form, and I don't want to have a fraction embedded inside my exponent. So this is now in logarithmic form. I'm going to switch this. This is going to be my base is e. Remember that a logarithm is an exponent. Is means equals. So this is my exponent right here. This 0.2t is equal to the power, which is 80 divided by 100 minus b. And again, my job is to solve for b. So I could cross multiply and then divide, or I can just put a 1 over here and then swap these corners, which is what I'm going to do. 100 minus b is equal to 80 divided by e to the 0.2t. And now to solve for b, let me see here, what do I want to do? I think I will subtract my 100 from both sides of the equation. However, that's going to leave me with a negative b. 80 divided by e to the 0.2t minus 100. I'm thinking I want that e to the 0.2t here to get out of there. Can I clean this up slightly? Can I call this 80 e to the negative 0.2t and then minus 100? And now I divide through by a negative 1. This will give me, let me see, I'll just do this for you. Gives me b equals negative 80 e to the negative 0.2t and then plus 100, which would be really sweet, wouldn't it, if I turn this around and I said b of t is now, write the 100 first, and then minus 80 e to the negative 0.2t. And that would be the end of my problem. Notice how I switched from b to b of t. The function is b, but it's also a function of t, so those notations are interchangeable in this problem. And we are done with this problem. Okay, let me see, did they ask us to find anything else? No, it just says use the separation of variables to find the particular solution. So we worked through a lot here. Okay. Listen, just as a sidebar, before I say I'm finished with this whole process, I am going to go down here and I'm going to just talk to you about a proportion. We could have a proportion. We could have a over b is equal to c over d. And I can cross, I don't like that d. I can cross multiply this proportion, which means anything in the denominator is going up to the opposite corner. And this is going to give me AD is equal to BC. Well, anything that results in the same cross product is a legal move. So I could take my A and my D and I can interchange them. I can swap these two corners right here. Those two things, I can swap those and it would still end up giving me the same cross product that I had before, right? This is still going to give me AD equals BC. I can swap the top left with the bottom right, or I could actually swap I could leave the A and the D all alone, and I could swap the bottom left with the top right. So I could put a B up here and a C down here. When I cross multiply here, I'm still going to get AD equals BC. So this is super, super helpful when you have a question like, I don't know, like 5 equals 2 over x. You can just put this over 1, swap these things, and say x equals 2/5. Now I know you can do a lot more work than that. You could say 5 equals 2 over x. You can put this over 1 and you can cross multiply and say 5x equals 2 and divide by 5, and then x equals 2/5. You get the same answer. Whoops, 2/5, not 2/3. You get the same answer, but it is kind of neat, especially when things get complicated, to know that I can swap corners of my proportion anytime I want, no matter where they are. If I want to swap them from here to there, or if I want to swap them from here to there. I can actually swap them both if I felt like it. I started with A over B equals C over D. So I could put my A down here and my D up here. And I could, instead of my B down and below, I can put it up high and my C. This still gives me the same thing. I still end up with AD equals, oh, that was so silly, Gina Marie, BC. So I get the same cross product no matter what. All right. Getting out of variables and everything just for a minute. I'll show you one thing with a set of numbers and see if that makes sense to you. Let's see. I'm going to just think of a couple of fractions that equal, let's say, 2/3. If I times by 3 and by 3, that gives me 6 over 9. So 6 over 9. But if I times by 4 over 4, that gives me 8 over 12. So this is true, that 6 over 9 and 8 over 12 are absolutely identical. And it's true because they both reduce down to 2/3. You could prove it that way. Another way you could prove it is by playing with the cross products. You could say 6 times 12 equals 8 times 9. Isn't that true that 72 is equal to 72? Absolutely true. So let's try this. Let me see if it makes sense to you. Let's swap the 6 and 12. Put the 12 up here and the 6 here. Leave the 9 there, leave the 8 there. Is this true? Is this still a true proportion? I'm not saying it's the same proportion I had originally, but is it still true? And the answer is yes, it's still true. They both reduce down now this time to what? What do you think? If I divide this by, what I got to divide by 2 and 2, they both reduce down to 4/3. This would also reduce down to 4/3. But better yet, 6 times 12 is 72. 9 times 8 is 72. It still checks. It still works. Anyway, I just thought that that whole concept merits a little bit of attention, and I will get rid of all that at this point. Let's say goodbye to everything, and let's end our lesson here with, of course, something. You know what it's going to be, don't you? It's going to be something that says, talent out. Whoop, whoop.